Hello everybody, welcome to the latest edition of the Physics Corner, a series of videos in which we help you set up and solve introductory physics problems. I am your host, Dr. Christopher Cirola. Today we're taking a look at sound waves, specifically waves on a string. So, when we talk about waves in a string, and in this particular instance we'll be using a guitar string as our example, the string itself is tied at both ends. Or, if you will, one end is tied and the other is using a finger to pull the string over a fret. In either case, same kind of issue. So we have a string tied at both ends here and here, you can imagine. So the length of the string then is from here to here. And that will be information we need to help us determine what kind of notes we're going to be playing. So specifically in this case, let's imagine we have a guitar player who's trying to tune a guitar string to middle A note, which is about 440 hertz. The string itself has a length of 60 centimeters or 0.6 meters, and the string that the guitar player is tuning has a mass per unit length of 0.32 grams per meter. That turns out to be interestingly important. What tension, physics tension in newtons, should be applied to the string to tune this to 440 hertz? Let's take a look. So with the string at a length of 60 centimeters, one thing we need to ask is what kind of notes or waves can fit in a string. Something that you should be aware of is that when we pluck a string like this, not every possible wavelength can fit in the string or will work in the string. And why was that the case? Well, if a wave comes like this but hits off at this end, that's not possible, right? If a wave starts here but say ends up at some point above or below this point, that's not going to happen because the string is tied to that point. So however a wave is going to fit, if you will, into the string, we have to have a 0 point here and here. Now you could have a wave that fits like this, half a wave could fit in. You could have one full wave, do something like that. You could have, say, 1.5 waves, and so on and so forth. Any multiple of half wavelengths that will do the trick. We're going to focus on what's called the fundamental or first harmonic, which is the half wave situation. And let me sketch out exactly what that means. So this is the actual guitar here and here. But imagine we want to put a wave into that. The first kind of wave, the largest kind of wave we can fit in between will look something like this. So imagine plucking the string, say in the middle right here. You pull the string up and it vibrates back and forth like this. The string must be here and here. It's tied. It has no options. It can't go anywhere else. Now, that's the largest possible wave you can have. If it was any larger, it wouldn't fit. But if you look carefully, that's really only half of a wave. If you were to sketch out where the rest of the wave would be, it might look something like this, right? Now, the guitar itself is here and here. There is no section here, but the wave doesn't know that, so to speak. And so we have half a wavelength fitting in that distance. And so what we can say about this situation is that the wavelength, or the original wavelength, we can call that the fundamental wavelength, is equal to twice the length of the string. Now, again, it is possible to fit other waves into this space, right? They'll have to be smaller wavelengths, they can all fit. But there'll be some multiple fraction, if you will, of this distance. So you can have one full wave in here, you can have 1.5 waves, 2 waves, 2.5, like that, if you will. But the longest possible wave that can fit is this one here. So what then do we know about the problem? We are given the frequency will be 440 hertz. And by the way, if you think about it, if this is the longest wavelength, that will be the shortest frequency, right? Okay. The string has a length of 60 centimeters or 0.6 meters. The string has a mass per unit length of this many grams per meter. So let's write that out. The mass per unit length is given by the Greek letter mu. Notice, by the way, just as an aside, that this is a different usage for the Greek letter mu than you might have seen before. In previous episodes or in previous work in, say, physics with friction, you would have encountered mu as the coefficient of friction. Totally different usage here. This happens sometimes that there's overlap. There are many more concepts and quantities in physics than there are letters, even if we include the Greek letters. So just be aware that this particular symbol here does not refer to friction. This is specifically referring to a different concept, which we're calling mass per unit length. But assuming we'll do that, mass per unit length is 0.00032 kilograms per meter, because we do want to put this into standard units, it turns out, like that. Okay, those are the facts that we're given. What don't we know about this? Well, we don't know the speed of the vibrations. How fast will the wave be shaking back and forth? That's not given. It might turn out that we need to have that number. In fact, we'll make sure to calculate it. And of course, the thing that we're looking for in the long run is the tension. And we use capital T to stand for tension. By the way, this also is a repeat letter, if you will. We've seen capital T stand for period. We're seeing it here stand for tension. Again, that happens sometimes. The way to tell the difference, what letter is being used for what idea, is by context. In this case, we're talking tension, T for tension. Okay, period is not a question we're asking at this stage. If we were to ask about period, we'd have to use a different letter, right? And we could do that. We use whatever letter we want, as long as everybody agrees on it. So, what should we do to set up this problem? Okay, so first of all, this is the speed of vibration that we're going to be talking about, not the speed of sound, say, in air or in some other substance. So the speed of sound in air is about 343 meters per second. But that's not the speed we're solving for here. The speed we're solving for here is how fast the string vibrates back and forth. That's what's going to become useful for us in this particular problem. Okay, but with that being said, the speed of this wave, if you will, or this shaking back and forth, is still calculated in a similar fashion to wave speeds for other quantities in other situations. In other words, the speed of wave is still wavelength multiplied by frequency, like that. Okay, so what is the wavelength? The wavelength is twice the length of the string, as we discussed before, and a frequency is given. So 2 multiplied by 0.6 meters, and then 440 hertz, like that. And if we do a little bit of figuring, we come up with a number of 520 meters per second. Okay, again, that is the speed of the vibration of the string itself in this situation, not the speed of sound once that vibration affects the air. That's a separate question. And that would affect, say, the wavelength of the sound in air too. But this is not what we're talking about. In this situation, we're talking about the string, not what you hear from the string, but what the string itself is doing. That's why we're talking about this way. All right, what else can we say about the speed of the wave in the string, and how can we relate in the tension and the mass per unit length? Where's that coming into play? So another way to talk about speed in a vibrating string is with this equation here. So the speed of a vibrating string is equal to the tension across the string divided by the mass per unit length, right? Now, we already have the speed, so we need to turn this around for tension. So square both sides, right? And we'll get v squared equals t over mu, like that. And then, of course, multiply both sides by mu, and we'll have t equals mu v squared. And that will be the way to solve this. So let's go ahead and put in our numbers for tension then. So 0.00032 kilograms per meter. We have 528 meters per second, whole quantity squared, everybody. And when we do this, we come up with approximately 89 newtons. I'm rounding off a little bit, of course, but that gives you the right idea. So not quite 90 newtons, or if you prefer pounds, this is a little bit more than 20 pounds worth of force that's being exerted on the string. Gives you kind of a rough idea how much tension the string has to be under to make this particular note. Now, by the way, guitars in general have more than one string, right? So there are many strings. Each individual string on, suppose, for example, a 6-string guitar has a different mass per unit length. That's sort of the point. And that makes them capable of different notes, right? So if I have a different mass per unit length, that would ultimately give me different speeds and different tensions, which lead to different frequencies and so on. So you can play the same note on different strings, but one of the ways to do that, to accomplish that, is to use different lengths of the string. That's what your fingers are for, and different tensions in the strings. So guitars and many other musical instruments are fairly versatile in this way. Also, one more thing to remind you of, we are finding here what's called the fundamental wavelength or frequency, the largest possible wavelength, therefore the smallest possible frequency that fits in this distance, in this space between the tied ends of the string. That is not the same as saying that's the only wavelength, though. There are many other wavelengths, again, that can fit, and they will blend together. And in fact, that's what gives you the overall kind of pitch or sound that you experience. If you actually pluck a string in this situation, you will not only hear the 440 hertz. This will actually be a blend of several different wavelengths and frequencies together to give you that characteristic sound that an individual guitar string might make. So just be on the lookout. If you try playing a guitar string, you don't get just one note or one pitch out of it. You get many blended together. With all that being said, that's the tension that you would come up with. All right, everybody. Technical support, as always, comes from Sidney Gautraw and Sophia Turner. Funding for this project is from the University of Mississippi and University of Southern Mississippi. These videos are filmed in Hattiesburg, Mississippi. Extra support, we went ahead and cheated a little bit. We checked into an online source to help us with the guitar parts. OmniCalculator.com is a nice resource for that sort of thing for musician types. And I am your host, Dr. Christopher Cirola, thanking everybody for your attention, and clear skies as always.